All right, we just spoke about the interval of convergence for your Taylor series. Let's define that. We did define the interval of convergence. Let's look at this theorem so that when we go to examples, we can determine what the interval of convergence is. So that's really the nature of the problems we're going to see. We're going to be given the Taylor series. They're just going to tell us what the Taylor series is. We're going to have to figure out the interval of convergence. Okay, so here comes the theorem. The infinite series, the Taylor series right there, from k equals 0 to infinity, a k x to the k will always converge at x equals 0. So if we are centered at 0, like we are here, then we know we at least will converge at x equals 0. So that will be the center point of our interval of convergence, if that makes sense. How do we know that we will always converge at x equals 0? Well, let's think about it for a second. If you take 0 and you plug it in for x, well, wouldn't the whole thing just become 0? And then we're still going to think infinitely many terms, but it would just become 0 plus 0 plus 0 plus 0, right, dot, dot, dot. You just be adding these zeros, and what's that all going to add up to? Well, 0, and 0 is finite. So we know that for x equals 0, that our Taylor series will converge, at least there. But how are we going to find, like, what's the interval, on either side of 0? Okay, so here's what the theorem says. Consider your coefficient. So we call it AK here. We're going to consider the coefficient for the nth term. Okay, AN equals the nth derivative of f evaluated at 0 over n factorial. That's the coefficient of the nth term. Okay. Turns out there are 3 cases for AN. Case number 1. Perform the limit as n approaches infinity for AN plus 1 over AN. And, we're going to do examples here, so we're going to see exactly how to set all this up. When you perform that limit, and remember there's an absolute value, after performing that limit, if we get L, which is greater than 0 and finite, then the interval of convergence we will know is this. It's the interval from negative 1 over L to 1 over L. So you notice a couple things about the interval. 1 over L is, of course, the reciprocal of whatever number we get here. So we'll take the reciprocal, and it'll go from the negative of that reciprocal to the positive of that reciprocal. What is the center of that interval? Well, it's 0, right? 0 is at the center, and we move 1 over L in each direction. Think of it that way. Okay. Now, if you would like to know why that turns out to be the interval of convergence for that answer from this limit, then, hey, ask me in one of the Zoom meetings. Maybe we'll talk about it at the end after we answer some other questions people have. I'll be happy to tell you, although I find most people, they don't really mind. They just want to know what to do, which is all you need to know in the end. But if you would like to know why this is the case, I can certainly tell you that too. Also, I probably should have said this a moment ago, when we're doing this limit, AN plus 1, that is the next coefficient following AN. It's the n plus 1th term, the one after. So we take the ratio of consecutive coefficients. That makes sense. So if the limit of that ratio of consecutive coefficients is a positive finite number, then we get such an interval of convergence like that. Okay, what is case number 2? Well, we're still going to perform the limit as n goes to infinity for the absolute value of the ratio of AN plus 1 over AN. But what happens if we get 0? Well, it turns out that the interval of convergence in that case is all real numbers. It will always converge no matter what the value of x. In other words, every value of x would cause the function to equal that Taylor series. It's always going to work out to be equal. Okay, from negative infinity to positive infinity. And case number 3, you might be able to guess what it is. What if, when we take that limit, n goes to infinity, the ratio of an plus 1 over an, what if our answer equals infinity? So we've got the 3 cases, right? Positive, finite, 0, and infinity. Well, in that case, well, it's kind of like the opposite of case 2. The series will only converge at x equals 0. So it does work at that one number, but nowhere else. Okay. All right. We've got all the theory. Let's look at our first example. We've got 3 of these, just to highlight different things that we might encounter. Okay. So the question is, find the interval of convergence 2 over 3 minus x. And it's so nice, and all the questions we see, they're just going to tell us what the infinite series is. And they even do it in the expanded style, which is nice. This should have a plus ... on the end, by the way. Okay, so it turns out the function 2 over 3 minus x is equal to 2/3 plus 2 over 3 squared x plus 2 over 3 to the third x squared plus, and we'll just keep going in that same pattern, keep taking the next power of 3 in the denominator there, keep raising the powers of x. This is the nth term, and parts of this are kind of small. 2 over 3 raised to the n plus 1 times x to the n plus ... So we notice the power of 3 is always 1 more than the power of x, right? So squared into the first, to the third, and squared. But they tell us that already. We don't have to figure that out. Okay. Well, what are we going to do here to find the interval of convergence? We need to identify that nth term. Luckily, they tell us that already. And then we need to just pick that coefficient right there. an equals 2 over 3 raised to the n plus 1. The coefficient of the nth term. Okay. Once we have an, well, we need to know what an plus 1 is, because we're going to take the limit of this ratio. So how do you find an plus 1? Well, if you have an, it's just as simple as replace the n with n plus 1. And that'll get you the next term. So it's 2 over 3 to the n plus 1 plus 1. Of course, we're just going to go ahead and simplify that to 2 over 3 raised to the n plus 2. Okay. And now to use our interval of convergence theorem. And I'm showing you the first step here. We'll just focus right there. We take the limit of an plus 1 divided by an. And we've got that absolute value as well. That's important. So I've got 2 over 3 to the n plus 2 all over 2 over 3 to the n plus 1. So it turns out this is going to simplify nicely. That's going to be the case in all of these. But it's a matter of getting there, right? So what most people do as a first step, because we've got this big fractions for an, very, very common. That's going to be in almost all problems you see, if not all of them. This fraction over a fraction. We're just going to take that one on the bottom and flip it and multiply. So that's what you see over here. So there's my an plus 1 times, and I flip the an to make it multiply, and I can see the cancellation a lot easier that way. So 2 over 3 to the n plus 2 times 3 to the n plus 1 over 2. And we can see some of the cancellation already. Here's what I'd like to do. I'm just going to rewrite the 3 raised to their powers, okay? So 3 to the n plus 2, think of that as 3 to the n times 3 squared. Now, if you're familiar with the laws, the rules of exponents, right? If we have the same base when we multiply, we add exponents. Well, why not work backwards? 3 to the n plus 2 is 3 to the n times 3 squared. And I'll do the same thing over here. 3 to the n plus 1 is 3 to the n times 3 to the first. And hey, think of it that way, doing it like that, we really get some good cancellation, right? Obviously the 2's cancel, but then 3 to the n cancels. And then we've got, 3 over 3 squared. It's just going to give us the limit as n approaches infinity of 1/3. And of course, the answer to that is simply 1/3. Hey, we got our limit. And now we just got to think, which case are we in? Well, this is case number 1. That's a positive number, and it's finite. So in order to get the interval of convergence, we're going to take the reciprocal. It's -3 to 3. And there it is. We got it. So just kind of think back on this. This function will equal this Taylor series, but only for values of x between -3 and +3. So, if we picked 1, x equals 1, and plugged it in here and plugged it in there, and started adding up terms, the more we add, the closer it would get on this side. Actually, if x equals 1, that whole thing's going to equal 1, isn't it? So if we plugged in 1s for the x's and kept adding them, or if we plugged in 2, it would work out that way. But if we were to plug in something like 5, we go outside of that interval, then these are no longer going to be equal to one another. Let's stop this video right here. In the next video, we'll have parts B and C.